Okay, you can see that I have drawn a picture on the screen. And here is an oven which produces the silver atoms in a heated state, and that shoots off in this line. And here is a Stern-Gerlach apparatus, and I have drawn it like a box, but this orientation is the orientation of the magnet. Okay, and you can see that the orientation is not exactly in the z direction, it is at an angle θ1 with the z direction. So I'm considering any arbitrary spin state. That means this spin preparer blocks off one beam and allows one beam to pass. So that is basically, it has been prepared in the state A, which is up in this particular direction. Okay. And then that beam passes through another Stern-Gerlach apparatus. And this time it is an analyzer because we will observe the result. And it is inclined at an angle θ2 with the z-axis. So these two are in any arbitrary direction. And we will try to figure out what will actually be observed here. Okay. So that is the task we will take up today. So this is this is oriented in the n direction. This one is oriented in the n direction. So it measures the spin in the n direction, Sn. Okay. And so this measures spin in the n direction. So that is Sn, as we have denoted earlier. And it has the spin in the n direction, this operator in the n direction has eigenvalues, eigenvectors. N and eigenvectors are up in the n direction and down in the n direction. These are the two eigenvectors. So this is what this guy does. And it has been prepared in the state A. So effectively what we have to do, we have to figure out the projection of this state onto these states, which will give me the probabilities of finding up or down, right? So let us express A then, A as a linear combination of up n and down n. Let us call them A up is a coefficient up n plus A down n. Okay. So we have expressed this vector as it comes out, its state, as a linear combination of the two eigenvectors related to this observer. Okay. Now, what will be the probability of observation in the up state and the down state? Basically, these. So probabilities will be, I'll write here so that I have space. Probes will be mod AU square and mod AD square. These are the probabilities of observing, and that's what we're trying to find out now. So let's try to find out AU. So AU will be the projection. So projection onto up n of the A vector. It will be AU. It will be, sorry, up n, which will be 1 plus AD it will be up n, down n. So obviously this will be 0 and this will be 1, and therefore you get A. So this is a way of obtaining the coefficients which will give these probabilities. Okay. So similarly, AD is nothing but the projection on down n. And the probability of finding up is just the squares of this. Okay. Now spin analyzer is at an angle theta2 and spin preparer is at an angle theta1. So we can write, we have already seen that a vector in a particular direction, a spin prepared in any particular direction can be expressed as A, it is at an angle theta1. So, and theta is there, but phi is 0 because it is flowing in the y direction. So we can express that as the way we have written in the last class, cos theta 1 by 2 and sine theta 1 by 2. And in a similar way, up in the direction of n will be written as cos theta 2 by 2 sine theta 2 by 2. Okay. And now we have to take a projection here in order to find the probabilities. So projection of this and this, that is easy to find. What I'll do is, I don't have much space here. I'll just now delete this picture and we'll carry on. Okay, now then it is, we are trying to find out up n A. So up n, this is a bra. So we have to turn this into a bra. So it will be cos theta 2 by 2 and sine theta 2 by 2, a bra, a row vector, and cos theta 1 by 2 sine sine theta 1 by 2. I have to conserve space. So this is equal to cos theta 2 by 2 cos theta 1 by 2 plus sine theta 2 by 2 sine theta 1 by 2. This is equal to, it's easy to see, is cos theta 2 minus theta 1 by 2. Okay. And the probability is mod square of this. So probability of up, I can write, is equal to up n A square is equal to cos square theta 2 minus theta 1. This is clearly the cos square theta by 2 rule, because the difference between the preparer and the analyzer is theta 2 minus theta 1. And that is what we earlier saw, that has been observed. And now it is clear that the theory, very simple theory that we have developed, explains why there is a cos square theta by 2 rule. Okay. Similarly, the probability of down will be sine square theta by 2. So that's this is how we sort of ensure that the theoretical structure that we have developed. You might have noticed that along the way we have made some assumptions. Assumptions like, for example, the spin angular momentum in some sense follows the properties of the orbital angular momentum. For example, the commutation property and things like that. We assumed that they behave the same way. And now that we are able to arrive at the experimentally observed answer, we know that we were on the right track, that these things are truly valid. Okay, so let's continue. Let me delete this. Let's continue. We would also like to calculate the expectation values. Expectation values. The expectation value of the spin angular momentum. You know that some of these particles will be ultimately observed with a spin angular momentum plus h cross by 2, and some of these will be observed with a spin angular momentum minus h cross by 2. So what is the expectation value of spin angular momentum? So that is basically Sn, its expectation value. It is the probability of observing up times h cross by 2 plus the probability of observing down times minus h cross by 2. Okay? And this is, as we have seen, basically mod of n a square h cross by 2 bracket plus, or you can put a minus sign here by bringing this minus up front, minus down n a square. Good. So we earlier have learned that expectation values are to be obtained by sandwich integral. Does it work here? For example, expectation value, can it be written as, say, it was in state A, Sn operator A. Can we write it like that? This is an easy way of writing it because we can easily see that that will work. So we need to figure out if this is equal to this. Because in case of wave mechanics, our state was psi here. So we said psi, the operator, psi, and this sandwich integral will give the expectation value. Does it work in case of spin? So let us try to work out. Firstly, let us write something here at the end so that we have no difficulty with space. A is, it is AU up n plus AD down n. Okay, that was A. So our A bra will be AU star, sorry, it will be bra up n bra plus AD star bra down n. So this side is done, that side is done, and Sn will be sandwiched in between. So, and also we have seen that that these, let me write, n and down n are eigenvectors of Sn with eigenvalues plus h cross by 2 and minus h cross by 2 along the n direction. This is the observer is this, and the observed, if it is in this state, it is guaranteed to have eigenvalue or guaranteed to be observed in this with this value. If it is this state, is guaranteed to observe in this value. So these are the eigenvectors with these eigenvalues. This is something we know. So Sn operating on a ket will then be the h cross by 2 will come forward by 2 here. Au, it will be up n A is this, Sn applied on this. So if you have Au here, Sn applied on up ket will give plus h cross by which has come forward. Sn applied on down ket will give minus h cross by 2, so it will be minus Ad down n. Okay, is the logic clear? So we are applying this on this state. So there are two parts. This will give a eigenvalue which is h cross by 2. This will give another eigenvalue which is minus h cross by 2. So this will be written like this. And so this, the Sn expectation value is a bra Sn operating on A. Now A bra is this, so it is A up star bra up n plus A down star down n. This is the bra part, and the ket part is this. So I'll keep the h cross by 2 up front, and then it is A up n minus A down n, and this immediately gives h cross by 2. This and this is up and up, so this gives 1. So A up star A up plus up down will cancel off because up and down their bracket gives 0. Down up their bracket gives 0. Down down their bracket gives 1. So this is so it will be minus A down star A down. So this is equal to h cross by 2 mod A up square minus mod A down square. Okay, this is the same as what we earlier observed. So we can see that this is also a perfectly valid expectation of the expression for the expectation value. So this can be expectation value can be calculated this way or this way, and depending on whichever way it is convenient. Okay. So this is regarding the expectation value. You may be given problems where you are you have prepared the state in a the particles in a particular state, and you are now analyzing through a Stern-Gerlach apparatus, and you have to calculate the expectation value of the spin when it reaches the detector. Good. So at this stage, I'll stop for a minute, and if there are questions, and then I'll carry on. Is there a question? Are there questions on this? We have basically shown today that the formalism that we have developed, pretty simple formalism, I should say, much simpler than what you are learning probably in classical mechanics. Quantum mechanics, its mathematics is much simpler than that of classical mechanics, but that's how it is. So we have shown that it works for predicting the probabilities, and it also works for predicting the expectation value. If there's no question, let's go ahead. Now we'll talk about the energies contained in the spin. Let us start by again drawing analogy from orbital angular momentum, about which we have learned quite a bit. In fact, when you said that you need me to repeat the orbital angular momentum part, I was actually relieved, because so many times we are having to refer to the orbital angular momentum part that if I only detect dependent on your memory from the last semester, then sometimes I may lose you. But fortunately, I did that, so that's good. So we know that the orbital angular momentum, angular momentum that was designated as L, and the resulting magnetic dipole moment I did that some time back, so I'm writing it. Otherwise, I would have simply said moment that was designated as mu, if you recall, are related by mu is equal to a gamma L, where this gamma was the gyromagnetic ratio. This is something that we did earlier. And what we'll do is that the gamma is actually, that depends on the charge to mass ratio. And for electron, which is a negatively charged particle, this gamma is negative. Okay. For an electron, the gamma is negative. For a proton, the gamma is positive, and so on and so forth. Now, for the spin, we assume a similar behavior. For spin, we assume that the dipole moment due to spin is dependent, is proportional to the spin angular momentum. Here it was the orbital angular momentum, the spin angular momentum, and there is a proportionality constant. Let's call it spin gyromagnetic ratio. Okay, so this is spin gyromagnetic ratio. Okay, so so this is how the spin and the created the angle, the dipole moment created by spin would be related. That's simple. And if you place such a particle in a magnetic field, and if the particle is not oriented exactly in the direction of the magnetic field, there will be a potential energy. That potential energy will be, let us call it E mag, magnetic potential energy, due to spin, is minus mu dot B, and we are now trying to calculate it for the spin, where mu is this, so we can write it as minus gamma S dot B. Okay, and if the magnetic field is in this direction P, and if a unit vector along the same direction is, say, n, this unit vector, then the B can be written as B is some number B in the direction of the vector n. Okay, so again let's substitute it here. That will become minus gamma s, again B n dot s. Okay, and this can be this is basically the projection of s in the n direction. So it will be minus gamma b s n. Sn has the same meaning that we had considered earlier. So this can be, it is clear that the total potential energy due to spin is related to the Sn, and the way we do, let me delete this. The way we do everything in quantum mechanics is that if we want to obtain the operator for this energy, then we'll have to convert this part also into operator. These are numbers, that this is an observable, and therefore we'll convert that into an operator. So, so Sn is the component of the spin in the direction of the magnetic field. So the Hamiltonian operator in this case will be we are not considering a moving particle, so they will not consider the kinetic energy part. So we are only considering the potential energy due to this. So Hamiltonian operator H operator then becomes minus gamma s b. B is a number, and Sn now becomes an operator, and this operator is something that we know. So this we can substitute to obtain minus gamma s b. It had h cross by 2 up front, so h cross by 2 comes, and I simply write the expression that we written in the last class of Sn. It was, if you recall, you can check your copy for the last class, cos theta e to the power I phi sine theta, and here it was e to the power I phi sine. This one was minus cos theta. Okay, so we have obtained the Hamiltonian operator for a particle with spin. The Hamiltonian operator comes out to be this. Like any operator in the spin domain, all operators are a 2 by 2 matrix, so things are simple. Okay, and in the spatial case where the B is oriented in the z direction, then this term will be 0, and therefore in the spatial case B is in the z direction, then it becomes simple. Then your Hamilton simply becomes, the primary terms will be there, minus gamma s b h cross by 2, and then it will be simply this will be 0, so 1 0 0 minus 1. Oh, this is effectively, then it becomes minus gamma s b h cross by 2, and this is something that we know. This is sz operator. So in the spatial case, it becomes very simple, but in general, we'll have to consider this. Okay. What is noticed is that the Hamiltonian operator is a simple proportional to the Sn operator. And if these are two things that have a simple proportionality, must have the same eigenvectors. And we know the eigenvectors of this, and therefore we immediately know the eigenvectors of this. So this is how we proceed. I'll have to get some space. I'll delete the things up there, but I'll keep this box. I'll also delete this. Okay. So now we see that H is proportional to Sn, and therefore they must have the same eigenvectors, and we know that up n and down n are eigenvectors of Sn operator. Therefore, they must be eigenvectors of the Hamiltonian operators also. So therefore, we can write the Hamiltonian operator operating on up n then becomes this term minus gamma s b h cross by 2 up n, and Hamiltonian operating on down n becomes this time it is plus, because it will minus h cross by 2, so plus gamma s b h cross by 2, and then is down n. So we have also been able to write the equations involving the Hamiltonian. Okay. Let us write it in this form. This is equal to the energy, this is the eigenvalue in the up direction, up n, and this is equal to the energy in the down direction, right? You see that this is Hamiltonian operating on up, and this is the Hamiltonian operating on down. Notice the similarity of these equations with what you learned earlier in the last semester, maybe, regarding the time-independent Schrodinger equations. There, the Hamiltonian operating on psi was giving, or psi a, Hamilton operating on a eigenfunction was giving the eigenvalue times eigenfunction, the same thing. So this is basically the time-independent Schrodinger equation in this domain, in spin domain. And it is clear that these are the energy eigenvalues, EU and ET, right? And it is clear that now I can afford to delete this and just get some space. It is clear that the energy in the upstate is this, energy in the downstate is this. And since for an electron, this is a negative number, this is a positive number, and since for an electron, this is a negative number, this is a negative number, so for an electron, particle, your EU is greater than ED, and for a proton, ED is greater than, down is greater than up. So you see, the spin actually creates two energy levels. Additionally, two energy levels. Earlier, we have seen various energy levels are there, but if the constant particle has spin, it will have additionally two energy levels. So basically, the energy levels will split. And there is also another advantage of having this. So what is the difference between the two energies? The difference, so the two energy levels are are separated by an energy delta E, which is the mod of gamma S and P H cross. So one side H cross by 2, H cross by 2, they add up. So it is H cross. We call it H cross omega, where this is called the Larmor frequency. Essentially, it is possible to excite a proton or an electron from one state to another, one spin state to another spin state, from down to up or down, up to down, by putting in energy. In case of the electron, it will, if you put in energy, it will go from down state to up state. In case of proton, it will go from up state to down state, and then it will release the energy, release the photons as it relaxes again, and the frequency of that radiation will be this Larmor frequency. That's clear. And in fact, that has various applications. For example, you have seen that MRI is used in regular medical practice in most hospitals, MRI. What is done? What is actually done is that if you are doing an MRI of your head, for example, your head is put in a chamber. That means you are put in a chamber where a large magnetic field is applied, about 3 Tesla. So about V is equal to 3 Tesla. If you want to get an idea about how strong this 3 Tesla is, this cannot be applied using a iron core magnet, because iron core magnet saturates at around 1.6 Tesla. So this has to be done with air core, and a huge solenoids have to be put to make a B DC, a constant B value of this. And the moment you create that, this term or this term, it depends on B. There will be no difference between the two energy levels if B is 0. That's another remarkable thing. And the moment you apply a magnetic field, the two levels separate out. And then if you apply a specific frequency radiation, which is basically a radio frequency, then it is possible to excite the protons from a up state to a down state. When it's excited, then it will slowly relax, and as it relaxes, it will emit the energy as electromagnetic radiation that can be absorbed, that can be observed, and by observing those, we make an image. Because the parts which have larger density of protons, that means the things that are at larger density, they will emit more, and the parts that are relatively less dense will emit less, and that way you can make an image. And that's how we make MRI images. So effectively, we use spin and what we have talked today in order to make the MRI machines. Okay. If you want to do a quick calculation for the proton, gamma S is around 4.26 into 10 to the power 7 hertz per Tesla. And B is say 3 Tesla. In that case, the delta E will be, delta E is here. It is, that is the H cross omega. This is the required energy of the photons. So this is the required energy of, and that will be how much? Delta E is this. So I have unnecessarily put this one. Yeah. So this will be we are trying to calculate the frequency that we'll need. So I will have to write the omega is something we are trying to calculate. So it is H cross by twice pi into omega by twice h cross. So this is basically omega by twice pi, and this is gamma s b by twice pi is equal to, if you just calculate using this gamma h, this b, then you can easily calculate that. It comes to 2.03 into 10 to the power 7 hertz, which is in the radio frequency range. So what is done is that this radio frequency is applied, and by applying that radio frequency, you excite the protons from the upstate to downstate, and then it relaxes, releasing the energy, and that's how you make the image. Great. The last thing, about 15 minutes left, we'll quickly go through that. That is, how does the spin state evolve? What we have written here are the time-independent Schrodinger equations. How does the time-dependent Schrodinger equation look? That is what we are trying to figure out now. That's the last thing that we'll need to do before we go to a different topic next week. That the time-dependent Schrodinger is normally I h cross. Now we normally d psi ddt. When you are talking about the spin state, it is not psi, it is spin state. Normal wave mechanics, the state is psi, but in this case we have to write spin state. So we have to write the spin state, say A. And that Hamiltonian operator operating on A. That is the Schrodinger equation for the spin state. In order to solve this, we'll have to express in a convenient basis. So we express it in the basis up n and down n. So if you express that in the basis, then the way we do it is that there is a initial wave function. If you recall, the psi had an initial value. We expressed that in the way you did the assignment. We expressed that initial in terms of the eigenfunctions, and then you wrote the evolution equation using the eigenfunctions, the coefficients, and a phase factor. Here, exactly the same thing will be applicable. So you can write initial. It will be some linear combination of these two basis vectors, and so we can write AU up n plus AT down n. Okay, so these are the this is the expanded form of the initial state vector in terms of the eigenvectors, and then we can write A at any given time is again the same thing. There will be this term, there will be a phase factor times this eigenvector. The phase factor is in the same way e to the power minus I, the energy. Energy in this case is E upper T by H cross, exactly the same phase factor times n, right, plus A down. You notice that we are doing exactly what you did in your assignment. E to the power minus I E down T by H cross, and this is down. This is how the state vector evolves with time. But in case of the wave mechanics, when you did it, in order to come to this state, you actually had solved this. Here we did not solve it. We just said that, yeah, we have done it earlier. We just apply the same thing. But a question, natural question may come to you, is that is it applicable in case of the spin state? Well, that can be easily checked by putting this here and here. If the left hand side and right hand side comes to be the same, we are done. So it is I h cross ddt of A. A is this. So A is, if I take this IH cross comes to the front and this has to be differentiated, so it will be AU, and then it would be minus I EU T by H cross, or T will not be there. Okay. Then it will be the same term, e to the power minus I EU T by H cross up, plus AD, this term comes to the front, minus IED by H cross, then e to the power minus IED T by down. Okay. Now let's see. This is EU here, AU here, and it is e to the power I EU T by H cross up N plus this is ET AT is this term, e to the power minus I E D T by H cross down. And it is clear that this is nothing but the Hamiltonian operator operating on A. So this is essentially the Hamiltonian. So what we are pointing out, that better to focus on this particular thing, which I'll block off. This is how the state evolves. This is how the state evolves. The rest is just a proof that it works, and I'll delete this. So the state evolves. The state, that means the spin state, evolves with time, and the way it evolves is essentially the spin components in the up direction and the down direction, they change with time, and the way the whole thing evolves is this. So from this you will be able to calculate how the spin evolves. Okay, I'll stop here. If there's any question, we'll answer, and then from the next class we'll start a different topic, essentially focusing on bosons, fermions, the difference between them, a few particles together, and things like that. So are there any questions on what I did today?
Excuse me, sir.
Yes, who is it?
Gurpahul. Sir, shouldn't there be a rotational part for the Hamiltonian, like s square by 2m, like there was for L square by 2m in the orbital angular momentum part? Shouldn't there be a rotational kinetic energy, like S square by 2m.
Yeah.
This we consider only the
We
potential
are
energy.
presently we have assumed that we are considering only the spin part, which is also true if the particle is static.
Okay.
Okay. So today we have developed it only for the spin part. Now, if that particle rotates physically, then there will be those additional parts.
Okay.
But if it is static, then it is only the spin part, and that's what we consider today.
Okay.
Huh? Any other that means there will be a situation where a particle like an electron rotates. There will be angular part, angular momentum part, orbital angular momentum part, as well as the particle has spin. There will be a spin angular momentum part, and you'll later see. Maybe I'll not cover that this year, and the next year in the advanced quantum mechanics you'll see that these two angular momenta can interact with each other. And if these two, orbital angular momentum and the spin angular momentum, interact with each other, they give rise to some effects. So you'll see that later. That is not included in this year's course, so I may not cover it. Any other question? Okay, so let's stop here.